Welcome back to this video series where I continue to talk about content contained in the book Introduction to Nonlinear Control. And in particular, in this video, I'm going to talk about content contained in Chapter 12 on Introduction to Differential Geometric Methods. And here in this particular video, I want to focus on three motivating examples, which will then allow you to study the chapter in detail and to understand the methodologies behind the motivating examples shown here. So to start with a simple example, we consider a nonlinear dynamical system, one-dimensional system with output. So here we have x dot is equal to x cubed plus u, and then the output y is equal to x. And the goal here is to stabilize the state or the output y is equal to x is equal to 0. Okay, one way to do that with methods we have already discussed would be through a linear controller design. So linearizing the nonlinear dynamics about the origin, leading to the linear system x dot is equal to u. Once we have the linear system, we can define a stabilizing controller. U is equal to minus kx for positive constant k. We plug that into our system and we can analyze the closed loop dynamics. Here in this case, the nonlinear closed loop dynamics, where we can calculate the equilibria of the closed loop dynamics and then verify asymptotic stability properties. And since this is a simple one-dimensional system, here these steps might not be obvious, but the calculations are straightforward. And in this case, then we get local asymptotic stability of the origin and the region of attraction, in this case, of the asymptotically stable equilibrium increases with the parameter k. So that's one option. Now, a second option would be to use nonlinear controller design. And in particular, what we could do is we could define a controller of this form, u is equal to minus x cubed plus v, where v is still to be designed, so a new degree of freedom. But by selecting u in this way, we can cancel this x cubed term here, leading us to the new closed loop dynamics x dot is equal to v, where v is still a degree of freedom. So now in this case, we can again select v as a linear controller. V is equal to minus kx, again for a positive constant k, and then the overall closed loop dynamics are going to be of the form x dot is equal to minus kx. And now this system here has a globally asymptotically stable origin, so not just a locally asymptotically stable origin. And we have achieved that now with this nonlinear feedback law instead of the original linear feedback law. How did we achieve that? Well, we used a coordinate transformation of the input, which then led to a linear system. And for that linear system, it is straightforward for us to design a controller, a stabilizing controller, which then also allowed us to analyze the stability properties of the now linear system. And we could achieve, in this case, global properties instead of local properties. And yeah, this is of course a simple system, one-dimensional, where these steps might be straightforward, but it's important to keep the steps we've taken here, to keep them in mind. Namely, what we did was a coordinate transformation in the input u, which allowed us to rewrite a nonlinear system into a linear system. So as a second example, let's consider now a two-dimensional system with x1, x2, again, nonlinear system with output y is equal to x1, and we have the degree of freedom here in terms of u. Instead of considering a change of variables or a coordinate transformation in u, we can also consider a coordinate transformation in our state x. So here, if we define z1 is equal to x1 and z2 is equal to x2 plus x1 squared, then again, maybe not obvious calculations, but straightforward calculations by taking the derivative of this expression here and plugging it into our system dynamics up here, we end up with z2 dot is equal to u, meaning linear dependence from z to u. And similarly, yeah, but even more obvious here, if we take the derivative with respect to z1, then also the corresponding coordinate transformation here in the new coordinates z is linear, so we end up with a linear system in the variables z. Once we have this representation, controller design for linear systems is, at least for this low-dimensional system, straightforward. Namely, we can define a linear controller. And here in this particular case, we observe that for k1 and k2 larger than 0, in the z coordinates, we get a linear feedback law. We can use the coordinate transformation here on the left to also get the feedback law in the original coordinates, but by verifying the eigenvalues of the matrix z dot is equal to az plus bu, we can check and verify that the origin of that system is asymptotically stable. So what we've done here is that we have defined a specific coordinate transformation going from x to z. This coordinate transformation, by selecting it in a specific way, meant we went from a nonlinear dynamical system to a linear system. And now we can analyze the linear system instead of the nonlinear system, and we can still observe that x going to 0 is equivalent to z going to 0, meaning the convergence properties are preserved. And another property which we can observe here is that the input-output behavior, there it is actually not important if we represent it through x or through z. Because here we simply are interested in the correspondence from u to y, which is essentially the same as going here from u to y in the nonlinear dynamics. Okay, a third example, now taking the nonlinear system, three-dimensional nonlinear system, but again, output y is equal to x1. Here we can also try to find a coordinate transformation such that our system becomes linear in the new variables. And in particular here, if we define our coordinate transformation in this way, and if we define an initial feedback law, similar to the first example, where we select u, but we add a new degree of freedom v here, and u is designed in such a way that particular terms cancel out, then we end up with this linear system with nonlinear output. So here again, through a specific coordinate transformation, we are able to obtain linear dynamics, but different to the example before. Now our output is nonlinear. We could also consider a different feedback law. So instead of using here the feedback law on the left, we can use this feedback law here on the right. That would lead to the dynamical system here in terms of the relationship of the states x and the new degree of freedom v, where now the first two components of our system are linear. The third component is nonlinear, but we have our output still linear. So we have essentially a choice to ensure that either our system is linear, but we have a nonlinear output, or components of our system are linear, but not all the states are linear, but the output remains linear here. So, in particular, if we want to summarize that, here we are able to partially linearize the dynamics. The internal or nonlinear dynamics, here in this case, so the x3 component, which are nonlinear, we actually see that they are not visible through the output y here. So what does that mean? Well, we essentially have this decoupled system here, only depending on x1 and x2 and the input, and also the output only depends on x1. So x3 or x3 dot is actually not visible in the output. And that's then phrased zero dynamics in the chapter on this topic. Additionally, we can observe that for our dynamics 1, so for this representation here, V can be defined in an easy way such that the origin set is equal to is asymptotically stable. Again, here we have linear dynamics, meaning designing V under the assumption here that this linear system is controllable is easily possible. And in that case, if we know that Z converges to 0 from the output, we also observe that Y is converging to 0. However, if we focus on the dynamics, if we focus on the dynamics 2 here, or the second representation, here it is also straightforward to define a controller such that y of t is converging to 0. Again, simply by focusing on these two components here, x1 and x2, and designing another corresponding v. But it is not clear if the origin of that system, meaning x1, x2, x3, if these three states are going to converge to 0, giving us an asymptotically stable origin. Okay, here it was probably not clear how these coordinate transformations were obtained, and I have simply given them to you as more or less an oracle, and it's wouldn't be straightforward to come up with them without further knowledge. However, with the coordinate transformation given, it should be straightforward, or through straightforward calculations, it should be fine to calculate and verify that they actually satisfy the properties highlighted here. And what we've done was feedback linearization, which was either input to state linearization or input to output linearization. The properties we need to discuss to be able to do that in a structured way is the relative degree of a system and the zero dynamics, which tell us if it is possible to actually achieve input to state linearization or just input to output linearization, and what happens with the dynamics which we cannot observe from an output. The concepts that I used to then achieve input to state linearization is a coordinate transformation, either of the state or of the input. And the constructive way to do that relies on repeated Lie derivatives. So if we have two functions here, lambda and f, then we can look at these objects here, which are repeated Lie derivatives. Lie derivative we have already seen in the context of control Lyapunov functions. But now in this chapter here, we will apply that concept repeatedly to take the derivative with respect to the function lambda, and then the inner product with respect to f. And then we can also calculate the Lie derivative of this new object here. Well, and that will give us results about relative degree, about zero dynamics, and how to come up with this coordinate transformation, which provide feedback linearizations. And additionally, they also provide a concept to study controllability for nonlinear systems, which you also find as phrased as accessibility in corresponding literature. Okay, and that concludes this presentation here, giving a quick motivation of the content contained in chapter 12, and then the next video will focus on output regulation discussed in chapter 13.